Hello everyone, my name is Dr. Aknawas. I am senior member of IEEE, currently associated with the Marine Engineering Department at Military Technological College, Muscat, Oman. I am going to present my invited paper with the title Unidirectional Shared Aperture or Monostatic Antenna with Wideband Interport Isolation Performance for the 5G simultaneous transmit and receive application, which is termed as STAR or in-band full duplex. I will proceed with this presentation like this. First, I will present some details regarding the motivation for this work. And the second thing is the hypothesis for this work. And then I will discuss some relevant previous works related to like in-band full duplex or simultaneous transmit and receive antennas. Then I will discuss the proposed wideband shear aperture or a monostatic antenna with a required number of ports for in-band full duplex application, its structure and its performance characteristics when it is driven by a differential feeding or out of phase circuit, the feeding circuit. And finally, I will conclude my this presentation. The first thing is motivation for this work. So the motivation for this work is to design a wideband antenna with wideband isolation performance, which can be used for the in-band full duplex communication. The in-band full duplex communication, which is sometimes termed as single channel full duplex or simultaneous transmit and receive communication, has the inherent or intrinsic potential to double the spectral efficiency or the number of bits per second per hertz or the throughput. However, the performance of in-band full duplex that is highly dependent on the effectiveness of the self-interference cancellation. So in in-band full duplex, we are transmitting and receiving at the same frequency or over the same bandwidth at the same time. So the transmit signal will couple to the receive port if we use the same antenna for the transmit and receive purpose. So we need to cancel the self-interference. This leakage from the transmit port to receive ports or the transmit port to its own receive port, that is called self-interference, and we must get rid of this, or we need to suppress this or cancel this self-interference so that the coupled signal is not there. The actual signal of interest which is coming from the remote transmitter should receive at the receive port. The such self-interference cancellation scheme are the techniques. They enable the receiver to retrieve the actual signal of interest. However, the effectiveness of these self-interference cancellation levels define the intended isolation. So how much we cancel the self-interference that will provide us the effective isolation between the transmitter and receive ports. Most of the time, very high levels of the isolation between the transmitter and receive ports of the same antenna is required because a very large portion of the transmit signal couples to the receive ports of the same antenna. So we need very high isolation or very high levels of the self-interference cancellation so that we suppress this leakage. So there are so many techniques and there are so many stages where this self-interference cancellation technique can be used to achieve high isolation. But for the first stage, that is the antenna stage or the RF front end, because most of the self-interference that should be suppressed on the antenna stage. Consequently, the antenna designed with the capability of high isolation over wider bandwidth, because if we use such antennas for the wideband communication, wideband applications, then we need to suppress this self-interference over the wider bandwidth. So this is the mechanism how the in-band full duplex. In-band full duplex, you can use a single antenna or one antenna, or that can use a separate antenna. But in both cases, both antennas, even I mean the bistatic, where we have a different antenna for the transmit receive purpose, we transmit and receive at the same frequency. But the real N-band full duplex is where we have a single antenna for the transmit receive purpose, and that is transmitting and receiving simultaneously. Now the question is, how much self-interference cancellation we need? As I mentioned earlier, the levels of the self-interference cancellation or the isolation, required amount of isolation depends upon the transmit power, because what is self-interference? That is the direct coupling from the transmit to the receive port. So if we have a more transmit power, it means there is more leakage, and of course that leakage should be reduced. I mean that coupled signal must be suppressed. Some without any complex nature of the transceiver, the required amount of the self-interference cancellation that can be effectively calculated from the amount of the difference between the transmit power and the noise power. So, for example, in this example, we calculated the received noise power, that is KTB, the thermal noise, and then the bandwidth of the system and the noise figure. So the required amount of self-interference cancellation, that will be the difference between the transmit power minus, or the I mean the difference between the two quantities, transmit power and receive noise power. So you can see, if we have a more transmit power, it means we need more self-interference cancellation, or the isolation. So the in-band full duplex transceiver should suppress the self-interference to the receiver noise floor, that is defined by P or N. Amount of the self-interference is the figure of the merit for in-band full duplex or the star transceiver. Residual self-interference cancellation degrades or reduces the throughput of the system, because the doubling the spectral efficiency is the ideal case where there is no self-interference. But in practical system, there will be self-interference, so the achievable throughput or the spectral efficiency, that will be reduced. Required SIC level depends upon the power and the bandwidth, as mentioned earlier. SIC is achieved at antenna stage, analog domain, and the digital base after analog to digital convergence stage. Nonlinear self-interference can be suppressed by nonlinear self-interference cancellation circuits. So you can see here, there we have a transceiver based on the monostatic configuration, and the cancellation mechanism is employed on two stages. First on the RF front end, I mean in analog domain or antenna stage, and the second one is in digital domain. And these two SIC, I mean amount of the SIC achieved on these two stages, that can provide high levels of isolation. I mean we can achieve isolation at multiple stages. Now the question is, can we realize antenna with comparatively wider impedance bandwidth, and especially with the unidirectional characteristics where we have a very high front to back ratio? And of course, in that case, radiations are in one direction. And the second thing is, with the same antenna, can we achieve high isolation over or across the wider bandwidth? Or that bandwidth means range of frequencies. So at least our antenna should provide high isolation over that impedance bandwidth of the antenna. So here is some relevant work. So many antennas, they are reported for in-band full duplex application, but most of the antennas, they provide narrow impedance bandwidth. Patch antennas, inherent characteristics of the patch antenna is narrow band performance, narrow impedance bandwidth, and the isolation is also narrow band. But the intention or the motivation for this work is to realize antenna which is wideband. I mean impedance bandwidth is wider compared to the previous counterparts, and isolation over that impedance bandwidth is high. So there are two motivations. One is wideband patch antennas with two ports, one port for the transmit, another port for the receive purpose. And the second thing is that receive port should be effectively decoupled from the transmit port over the wide range of frequencies, at least over the impedance bandwidth. So this is the proposed antenna. This is a stacked configuration where we have three layers of the substrate and we have two patches. So on the top of the first layer, on the top layer, there is a antenna which is capacitively fed, and it has three ports where we have a one port for the transmit purpose and two ports for the receive purpose. Then we have on the second layer, on the top of the second layer, we have another patch that is electromagnetically excited, or the parasitic patch, and on the lower side of the third layer of the substrate there is a ground plane to achieve the unidirectional radiation. So the radiation will be uh, on the top side. Uh, on the back we have a ground plane, so there is no radiation. So this will of course provide high front to back ratio. Now this antenna provides 10 dB return loss or minus 10 dB reflection coefficient bandwidth of 50%, which spans from 3 to 5 giga, or the bandwidth is 2 gigahertz. And this antenna can be used for simultaneous transmit and receive application if we excite the receive mode in the differential or the balance feeding. For example, if we drive the port 2 and port 3, which are the receive ports in this uh, um, configuration, then the coupling from the transmit port 1 to port 2 and from port 1 to port 3, that will be equal in magnitude. If there is a differential operation at port 2 and port 3, then this coupling can be effectively cancelled because there is a differential or out of phase operation through port 2 and port 3. If the differential operation is, I mean, perfect, then we can achieve very high isolation or the self-interference cancellation, which is defined by the, of course, the symmetry of the antenna. But practically, the achievable isolation levels are self-interference cancellation. They depends upon the performance of this balloon, which is a differential circuit. And by performance, I means the magnitude balance and the phase balance. Phase should be 180-degree out of phase, and magnitude should be same. So here is a just depiction that how the self-interference cancellation levels, they are defined by the phase and magnitude balance of the balloon circuit. In this work, a very nice balloon circuit which operates with good magnitude and phase balance over the required bandwidth, which is from 3 to 5, because our antenna is working from 3 to 5 gigahertz bandwidth. So when this is connected on the port 2 and port 3, as you can see in this simulation schematic, then we can achieve very high isolation. That is like more than 60 dB over the entire impedance bandwidth, and the peak isolation is in excess of the 80 dB. So this configuration will give us the 10 dB impedance bandwidth after 2 giga, and isolation is better than 60 dB across the entire bandwidth. So you can see this the performance S21, which is basically the resulting configuration when the antenna and the balloon, they are our balance circuit, they are interconnected as clear from this schematic. And S21, that is the coupling, that in minus negative 60 dB minus 60 dB, which is means isolation is 60 dB. The coupling and the isolation, they are reciprocal of each other. So in this work, a monostatic antenna means we have a shared aperture, same aperture for the transmit and receive purpose, that provides very high isolation over wider impedance bandwidth, and that wider wideband isolation performance has been achieved through the differential feeding or the balance feeding configuration. That feeding network provides the effective suppression of the self-interference or the self-interference cancellation to achieve this performance. This proposed antenna achieved uh, impedance bandwidth of 2 giga, which is 50%. And the second thing is it provides 60 dB, at least 60 dB isolation across the entire bandwidth of this antenna. So compared to the previously reported in-band full duplex or the simultaneous transmit and receive antennas with the shared aperture configuration, this antenna provides more levels of the isolation or self-interference cancellation, and also the bandwidth is more. I mean, SIC or the isolation bandwidth is more, and impedance bandwidth is more as compared to the previous designs. That is basically the contribution and the novelty of this work. Thank you so much for your attention. And if you have any question, feel free to ask me through the email shown here. Stay blessed.